Hi everyone, my name's Alex. This is my team. I was unanimously chosen to be presenting to you because, well, it's just this way. I'll try to make this interesting. We try to take the domain of DNA sequencing and its privacy concerns as a topic. And we are proposing an idea for a framework with quantum computing to make sure you have a privacy-conscious way of transferring data and processing data so that everybody can still enjoy the benefits of DNA sequencing and its diagnostics, but still not reap the disadvantages of it. So what we're proposing here, and Bob is just a general term for the receiver of information. But we have Alice, imagine a human called Alice, and she wants to sequence her DNA for the purpose of knowing if at any point in the future she's going to have any trouble, say, for example, stomach cancer. That's the case we've been working with. There's a single nucleotide mutation, so if you have it different in your DNA, that if you have say a T instead of an A, there is a 100% probability that you'll develop, or 99, you'll develop stomach cancer at some point in your life, usually around the 30s or 40s. So she wants to know so she can prepare for it and better develop curing or caring facilities. And with current technology, it's already supposedly possible to sequence your genome, not continuously, but almost, with a thumb drive. So you buy a thumb drive, it costs 1,000 euros, but it's very inaccurate. So, I'm sorry. The proposed solution for this, well, it's not very important. The proposed solution we give to this, and it comes to solve the problems with computing, because taking 3 billion base pairs out of a person and processing them against the database to find whatever problems you want to find is a very CPU-intensive, a very intensive algorithm to run. This is obvious advantage comes from applying quantum computing, which we've been learning about, to this process, which not only promises advanced parallel computation efficiency, but also power efficiency, so low power consumption with so amazing efficiency. So imagine we take advantage of this technology, we put it in a thumb drive with the said sequencer, and Alice sticks it in the laptop and reads her genome. What then? Then in her computer, she has access to a text file with all her bases, but completely dissected. So it reads in chunks, in very small chunks, 200, 500. She needs to compare this to assemble the DNA. So she needs to compare this to a reference, and she can still do this in her laptop because there's ways of doing it. So compared to a reference genome, it's publicly available. Although we'll talk later about some privacy concerns there also. So imagine she takes her DNA sequence and then she hashes it using what we found to be homomorphic computing. Gonçalo is our expert.
Homomorphic encryption is a type of encryption where you compute encrypted data. So usually you cannot do operations on encrypted data because it's encrypted. But with homomorphic encryption, you can compute encrypted data and get the encrypted result back to the user.
Yeah.
That's one key problem. And we will also like to use quantum computing for homomorphic encryption and decryption, or at least for homomorphic computation.
Yeah, because the problem with homomorphic encryption and computation is it's really intensive. It's very inefficient. One of the promises of quantum could solve this. So if we manage to get this working, and getting this working for a very large data set or sample, we can in principle, solve or replace RSA-based encryption. We can still have the computation power to achieve it. And then we have two models. This is only one model, because we had a very long fight about legal and moral concerns. So this is one of the models. You would have a central watchdog, which would be, say, a regulatory entity controlled by the government, or a such entity, that would have a database of the hashes of the minimally unique sequences of your DNA. And what is the need for this agency is to provide a system of notification. If your DNA ever gets stolen and anybody tries to do something or research something about you, you should have ownership of your DNA. And it's, as in the common days, it's not really hard to get any person's DNA with hair, skin, blood you shed everywhere. So this is going to be a problem in the future, certainly. And this is one way. 3 minutes, thanks, again. Okay, so then the central entity would have, so the hashes in the database, and it would compare the hash with the person. So it would say, okay, this person belongs to this, or this hash belongs to this person, and it's this person trying to compute her own DNA. This is fine. She's registered, passed through. So then it would send it to a hospital or a company that would be able to do this comparison for diagnostics, check out what differences, what anomalies are in the DNA, and then it would get it back. So Bob is the hospital. Eve, stealing the DNA of Alice in a dinner, would try to find, imagine Alice is Bill Gates, say. The DNA of Bill Gates is very important because one could find out he's going to have, imagine Bill Gates is 20 years old. You could find out he's going to have stomach cancer. He's a very important person. You leak it to the media. Suddenly, shares are to the ground. Okay, so Eve gets the DNA, computes the DNA signature, tries to do the request, but the company flags it as this is not the right person for this hash, so denies the request. The other model, some of us, find that having a central agency with a database of minimally unique hashes of DNA is a disaster waiting to happen. So we proposed a separate, which is the more simplest model, which is not having it. Science, genetics will still be public, and we would assume that the better we can do is try not to get the DNA stolen in the first place. Because having a database, give it enough time, it will be hacked. We don't know how, but it will. And it's a much worse problem for a database of 150 million encrypted DNA hashes to be leaked than it is for one DNA to get sequenced. So there's that. Lose the central watchdog, and then only the people with physical access to you could have access to the DNA you need. And the last part we need for the quantum, the last part we need quantum for is at Bob, at the hospital, is a way of scaling this sequencing technology, because today sequencing is done very seldom for very select people, usually cell lines, it's not even people anymore, by supercomputers. So this quantum would solve the parallel problem of matching every read of DNA to the reference very efficiently, and then you could have a very big database. Oh, and the last point I want to make is that at the end, if you have this in place, you could set up a system, of course this depends on the country, where each user would voluntarily, of course, only if he or she wants to, voluntarily submit her or his data to the government's research facilities, or research facilities in general, for statistics to be made on the data. So you could run then also something of the sorts of quantum computing to find, instead of manually, the way it's being done right now, find correlations between genes and phenotypes. And that's it. That's our proposition. I hope you like it, or you have questions for. Thank you.
We only have one mic for all the speakers, so please.
I can try to give it a shot. It's very close to things I've worked on. So I don't think for sequencing you really don't need quantum computing, because there are algorithms like based on indexing. You index the sequences and you can do everything you said you wanted to do without using quantum computing. So this is probably not a good application for quantum computing,
Okay.
except on the part which I don't know very much about, of doing the homomorphic computing. There I don't know, maybe, but on the part that you refer to, which is either building the sequence DNA or looking for parts in big databases, you don't even need a supercomputer. You can do it on your laptop or on something like that, because the algorithms are very good and they basically create inverted indexes of the DNA. So you can have all your ideas and don't be dependent on quantum computing, which probably anyway will take a few decades before it can do that, if it can do that at all.
Is there any trade with using these algorithms? Is there any trade?
The algorithms are very efficient. They are like yellow pages where if you know the sequence, you go, it's indexed by order.
Yeah.
And so you can find any sequence on time that is proportional to the length of the sequence. If you have a sequence with 100 bases, you can find it on time proportional to 100.
To the length. Okay, it's one dimensional.
They are very, very efficient, and the trade-offs are very, very, very small. So you don't need quantum computing to address that part. For the other part, which is encoding it and then performing computations on it, that I don't know, maybe. But there are also algorithms where you actually compress the data and then you perform the computation on compressed data. So maybe they can be used. But that I don't know how to.
Yeah, okay. Thank you. Anybody else? I would ask for your help, Professor Kuhn.
Respect me to disagree a little bit with you, because I do have, let's say, a genome sequencing company, and we do see that there's a huge potential. We're working on quantum computing, and we're absolutely not there what they're assuming, right? So we just started doing it, but anyway, it's diversity of opinions is always very good. You talk about also the central watchdog. Yeah?
Yes.
I also think that's kind of a forced idea. So what about blockchain kind of technology to store the data of everybody's DNA?
That's true. Blockchain is a great idea. I don't know if you agree, but actually it didn't come to mind, but yeah, that's a great idea.
Okay,
I think
thank you.
Yeah. Thanks.
So yeah, I have a question. So you mentioned that you use this neuromorphic computing, right, for doing the encryption of the data for coding. So can you elaborate a bit more on that?
Sorry,
You
neuromorphic?
use neuromorphic computing,
It's
right?
it's not neuromorphic. It's
sorry.
homomorphic. It's
homomorphic. Okay,
cryptology.
misunderstood then.
Homomorphic encryption. You apply computation on encrypted data, and the result is also encrypted and is sent back to the user, that only the user is able to decrypt it.
So basically, it's an idea where you add or you perform arithmetics on the encrypted data. So you never decrypt it to perform your computation. But apparently, the state of the art is really slow. It's really
It's slow,
inefficient.
it's hard to achieve because it's based on mathematical problems that are hard to solve, and using quantum computing for that purpose will be a benefit for sure.
Okay. I see.
You can also raise ethical
Just a
concerns.
little, very fast comments. Either on blockchain or your central watchdog, you'd have a problem that I'm not sure how you can fix, which is if I submit the DNA of another person before he or she does, how can you validate that it's not mine? Okay.
Basically, you would the default answer to a request would be denial. Only people registered to the company would be accepted. Of course, we have a tiny problem of the chicken and egg. So how do you register without sequencing? A simple proposal is the gene chip. So you don't really have to sequence a DNA to have a fingerprint of it. You can take select zones of the DNA, minimally unique to a person, such as a fingerprint is needed to identify a subject, not the whole body.
So I like the scheme very much. I also like the scenario very much. It's an important scenario: security, data security, and digitalization of society. So
Thank you.
And you have some different solutions you provided here. And I also like very much the homomorphic computing idea. So I wonder how the complexity scales. So we have seen exact search for an exact text takes only O of n of the length of the text. Or I think for local sequence aligning, you need a little bit more, but do you know how much it will scale then, searching for an exact sub-string inside a long string? Does it scale, let's say, to the power of 2 then, or so how does it then scale with homomorphic computing?
At least I'm not sure about that. Currently, homomorphic encryption works for small data. But that's why we are also approaching to have not only all the DNA sequence, but only part of that to be able to work.
There's
But
does it go up exponentially, or is it some polynomial thing?
with the homomorphic encryption,
Yes.
it will be exponential. Yeah.
Any comment from the audience? Okay. So I think we should thank our speakers.
Thank you. Yes.
Thank you so much. So I'm gonna now ask the next team, which is supposed to be the first, you guys, right? Yeah. So yes, Leon, Jürgen, Marcus, Mike, and Ernst. Obrigado. So I don't know if you guys are presenting any PowerPoint. You're showing the poster. Yes, yes, yes. Somewhere. Yes. Yeah, we had stickers somewhere.
Does it also work? Or does it also work? The microphone.
Yeah. Or are they? Okay.
Yeah.
Oh yeah, now it works. Thanks. You can like a manual.
Yeah, we will do it manually at the end.
Sure. So we're gonna do this in a very low-tech way,
Yeah.
as proposed initially. The stickers finally.
Yeah.
So all the participants were invited to do this in a poster. This was supposed to be in a small room, and then suddenly it's actually a ginormous room.
How
many engineers do you need to get a paper on a whiteboard? The future of computing.
So guys, the stage is yours.
Closer to the audience, just to give it a, yeah, sure. Give you guys a chance to.
Can I start? Okay, welcome to our newly found startup company. It's called SecMesh, and we are the owners of the company. And what we did was we were looking for a big problem. Like the first lecture of this Future of Computing course was about, yeah, you first need to have a really big problem. So we looked at a UN nations page to see which are the 10 biggest problems in the world. And we found this problem actually a really interesting one. And it's about central government that could be corrupt or not. And it was just like in the previous presentation that there was like a central watchdog which can sort of manipulate the data unknown of the users of it. So we would like to prevent the abuse of centralized systems by authorities. And another problem we saw and we found interesting is that there is limited access around the world for the internet. So in some rural areas, there is not much internet. So for example, if you're hiking in the mountains, then there could be no internet and you don't know where you are or where the nearest McDonald's is. And a third one, it's when there is a natural disaster. So like a few, almost daily, big natural disasters happen. And then also all the infrastructure is down. So in that case, you don't have internet, so you cannot contact really that you're in need of help or need some other emergency related stuff. So these problems we would like to solve. And how we want to do that, it's like with our goals we want to reach. So we want to include like a design that's inherently secure by design. So we don't want to make like a central authority. Some other things that we have written down is that we want no central dedicated network. We want a robust and resilient solution, an independent and unsupervised solution, and some more. And the biggest problem is with the centralized, like a centralized authority. Is that if I want, for example, to connect to the internet, I need to first connect to a Wi-Fi router that is connecting to a server with DNS on it. Then I need to authenticate myself before I can reach a page. And there are like a lot of steps which contain an authority that could be abused. So therefore, we came up with a solution, and it's called a meshed network. And we added some quantum mesh network on top of it to make it even better. So the idea of a mesh network is that, that if I am a person and I want to join the internet, I just look at which other people are around that are already connected to the network. Then I can log into the network. So I have internet, which is like distributed among the crowd. So that's the definition of a mesh network. We increased the functionality by adding quantum to it, so quantum encryption. Because if I want to connect to the network with the normal internet, you first need to send your key, so it's like asynchronous encryption. And if we can use quantum, we can make it synchronous. So if I want to connect to it, you need to have been entangled with another person. And then only between those two persons, the connection can really happen. So you really need to trust somebody before you can enter the network. So that's our main idea. At the moment, we still have some little issues. Because if we want to use the entanglement, our mobile phones need to be equipped with it. And at the moment, we haven't found yet the solution. So we are actually hoping for the scientists to come up with a solution. I think that's most of it, right? Should I add something? Yeah, are there any questions?
So the technology that your solution is based on actually exists already.
Yep.
And when you mentioned that one of the problems that you could tackle would be internet in rural areas. But in those areas, you lack the existing infrastructure. So like whoever comes in can connect to that existing infrastructure. I'm wondering what's the obvious application that you can use with the technology you are proposing? Like that's viable in terms of utility.
Yeah, we came up with a solution that if you want to send your medical data, for example, yeah, you really go to the doctor and then show your medical data. And then it's only shared between the two of them. But yeah, we think there are many more applications that can use that kind of technology.
So rural, I mean, I think now a little bit of Africa, because I know not that many countries in Africa, but let's say Mali. And what I do see there is that the wireless communication technology is really omnipresent. So payments, everything goes by smartphone. So how does your solution, map onto such a poor country? Yeah, but that's one of the things they do have is wireless communication, wireless technology. So is there some compatibility? So it's a bit related to the previous comment.
Yeah, at least. No, you can.
Yeah, well, so the idea is basically we want to remove as many centralized points as possible. So the idea is that devices would basically talk to each other without any central, how do you call it, broadcasting tower or so. So also, for example, in the example of a natural disaster, if these towers would be gone, that would not matter because people's cell phones or other devices would still talk to each other. So the idea that we are having is we want to remove all these central points as much as possible because that's also, that tends to be like a point of trust that you need to place in it. So that our idea was that you only trust like local devices and then you build like a chain of trust. That was our idea.
And how would they then communicate with each other?
Yeah, that is one of the...
If you don't know, that's fine to say. We don't know, but...
Maybe I can add something over there. Okay, so actually you made an interesting note. Of course, mesh networks by itself are not specifically new. We know these technologies can work. So peer-to-peer communication, and by, like in the picture, if you create a network that covers all the entities, we can all communicate hop by hop. There's nothing new about that. You know, we are aware of that situation. Maybe slightly back into the topic we actually try to present. The idea is not in the mesh. The mesh is already known. The idea lies in the fact that mesh networks suffer from potential other problems like trust. You know, why would I send my data through a party which I'm forced to send through? Well, I don't know if I can trust this person, you know. And there comes the interesting application of quantum and entanglement, where we actually allow to secure our data going over untrusted entities, because we know that physically, based on the rules of physics, these people, even if they would carry on our entanglement, are not able to actually copy or listen the data we're talking to. So it's more like the mesh networks already exist, but hereby we try to solve the problems of secure identification and secure communication.
Okay, thank you.
Hope that answers your question.
It was just a minor comment. The technology for these mesh networks does exist. It's used in military applications. So far it has had problems because it does not scale well, so it breaks down when you reach about 100 nodes or so. There has been a recent breakthrough. There is a new technology that apparently can reach many hundreds of nodes without breaking down because of controlled traffic. Actually, there was a recent article on The Economist that you may want to look into. Just for now, it's just for military applications, but as in all such cases, it's very likely that it will trickle down to non-military applications if it becomes cheap enough. So.
Thank you for your comment.
So anybody in the audience? Okay, so thank you.
Thank you, guys.
So the next team is number 4. Oh no, we've just gone through that. We've reversed these two, the order of these teams. So the next one is team number 6. Yes.
I can start. I can think we can use this one. Okay, it's okay. So this was an idea that we didn't had a team or something. This was on a break, so it works. We were discussing another topic, and suddenly this came up. And I look at him, and he looked at me. This might be a good idea, and this is where we are. So it started by bugs in software. So we all know that software have bugs, and with the complexity of software growing, and with the amount of tools that we have today to build more complex system and more complex software, also increases the amount of bugs that you will find out. Also, there is another trend that's now becoming, looking at microservice architecture, where people tend to reduce complexity of software by building small pieces, but they are trusting on other small pieces. When you put all these pieces together, even you have small pieces, the system is complex. So whatever trend you follow in software development, complexity it's there, and bugs and complexity, they will travel. So as you evolve with time, with complexity, also the bugs will evolve. I don't know if there is a mathematical equation for this, but it will be interesting to analyze how bugs evolve with the complexity. And so we discover, why don't we use machine learning and AI to debug like humans debug? You know that we have all these static analysis tools, dynamic analysis tools, predictions tools, but they all go to the fact they try to predict, or they try to look at patterns, or they try to look at deterministic ways or predicting the software. Here in our approach, it's a more humanistic way of debugging software. How do we debug software? So we build our software, we put it running, and the software crashes. A Stack Overflow, core dump. What do? We look at the logs. First thing we do, go to Google, search for that string, analyze, I don't know what is my odds. Might be a pointer, it might be a thread lock, and then we do experiments. Probably we do print lines.
We have our tools.
If we are more advanced programmers, we can do breakpoints. But we try and we experiment till we might find out the bug and try to solve it. So our approach is really creating a machine learning and AI that will debug like a human. So it will not try to predict, it will learn. So we will see a problem, it will try to get solutions, try to find out breakpoints, analyze the logs, and with this, it can learn and evolve with time. And this is also important because with this learning process, you can have two approaches. It's like developers. So you get a very specific developer on one program and you know all that program. So these algorithms can work on the same software for many years and try to understand most, or you can detect patterns between different softwares and between different running environments and try to find out patterns. And these patterns can fit the traditional and more traditional approaches like the static analysis or dynamic analysis. And this is, I think, more important because when we look at the future of computation and less formal methods of developing algorithms like we saw quantum computing or the neural networks, the formal methods of finding bugs probably will not apply.
Yes,
we saw some articles, how to try to debug a machine learning or a neural network, how do you debug a quantum computing. So I think that for these less formal methods, this more empirical approach to debug will be good to debug and find out bugs.
Yeah, basically it's all about humanizing computation. So what we did, to sum up, what we did was like talking and having a beer and say, yeah, I don't like to debug.
Yeah.
Who here likes debug?
So we're solving your pain.
You like debug? Okay, one.
One person.
So one person in terms of statistics, okay, one person liking to debug against the other one, so let's be democratic. So no, I don't like debug, and we have tools to debug already. So they can analyze your code, they can say perhaps you were having this error or stuff. But sometimes we already have the algorithm and it works, but not the way it was supposed to do. So this approach is like a program that could know your program, that could know that you want this output this way, that you want to write this thing this way with good practices. So imagine, I don't like to go to Stack Overflow and copy paste code. It's horrible, so I want this thing to do that for me. If it works? It works, but then 2 years later I forgot the project and I have to go to Stack Overflow again to solve the same problem. So with this we could be solving, I mean, it's annoying, it's a waste of time, and yesterday we had like this talk with Art that sometimes it's good to waste time, but I don't like to waste time. I like to do new things and to apply AI to this stuff, to embrace the limits.
The practical approach to debug. It's like humans. So I don't know if it is efficient or not, but till now, even with the static analysis, people still need to debug by hand or by breakpoint or by printing lines, depending on the languages. So
it's the best.
So it's really an empirical approach, and the key factor here is the machine learning and AI, because this can learn. And you don't need new software to learn, so you can look at the past and put this algorithm learning with already bugs that you already find out in the past. So you can go to a specific commit, you know there is a bug, and you can put this machine learning with the errors of the past. So I think the potential for this to learn is very big, because all the data is already there, and you can use this to debug new stuff.
Yeah, and the stakeholders are pretty broad, so you can have
Probably
developers,
during
scientists,
this process,
companies.
Yes, you might find out, because
Quantum computing guys.
the static analysis is based on patterns and how people can define these patterns to identify bugs. So probably, I don't know, if we put this running, probably can find out new patterns for us, instead of us mathematically trying to get to these static patterns.
For sure, it's the best debugging machine.
You guys probably now made it very clear why Microsoft bought GitHub.
So I assume you are engineers?
Yes.
Yes?
I mean, he is.
I'm an electronic
not me.
engineer.
And you don't like debugging?
Some years ago, but I work on software.
I'm a soon-to-be. It's not. I'm soon-to-be engineer.
So I'm curious, given that, okay, that would be life-changing for you, what would be the first step? What would you first teach that magic? Because AI is not magic, so you need to tell the AI to do
For
whatever
example, when we do debugging, there was this conversation that some guys do prints, so we print logs and stuff. The first thing would be like putting these things, doing prints on a background without us knowing to see the output. They will just do prints, and they will say, okay, you have an error here, just do this, and it will be okay. So I didn't have to do the print, for example. I mean, it's very common here, for example, is anyone here who deploys apps in Android Studio or no? So we have to do lots of logs and these prints and log this and why. So with this in the background, you just say, okay, I already run your code. There is this print that I found out. Just correct it.
I think the first experiment was to put this on a continuous integration environment. That's the only
So
way
you catch exceptions and solve the code,
We have several
really
inputs.
solve and
Yes.
really learn with your code. For example, you work in a company with big codes, and our idea is that this can learn your code, your typology of working. So it's not just to be applied in a general way; it can also be applied in a really very specific way. So he knows how your company works. So he knows that you don't want, for example, hundreds of lines to do the same function. So he tries to help you to reduce the
We
amount.
discussed this. We might have different inputs. You might have a Stack Overflow, logging,
Yeah, lots of features.
reading, going to the internet to see for patterns. So
I think that's a huge opportunity, but go and build it, because like I'm trying to understand how you would build that.
I mean, it's already pretty much done. We just still to deploy some stuff.
I know zero about machine learning and AI. but this
So-
would be good. I think the first step, like for example, try to compile a program, catch an overflow. Catch an overflow or catch a stack trace, and try to identify what was the cause of that stack trace. For example, small. And then you can start to manipulate the code to put the print lines, and this can quickly evolve to
So I really like this idea, but I think there's a lot of magic there that we haven't figured out how it's going to happen. So one of the things that I would like to suggest you is to think upside down, which is instead of looking at the bugs that you have, looking at the regressions that you might have in the future. So think about something that is currently working. So you have a big system, as you said, and you're messing with some small method that has a lot of invocations in a lot of places. And when that method changes, there's a lot of things that can break. And I think that's much easier to validate because you already have an output, something that works, and you just have to compare it with the new output instead of trying to figure out new stuff, which is a bit more complex. Just food for thought.
Yeah. I think there are already companies working on that regression prediction. So they look at the past and they try to predict if a change in the method, what will cause. So our approach is not really on that direction. It's really the humanization of the debugging. And for us to understand, you said, what's the magic? Yeah, you can ask every developer. He will tell you what's his magic. Then I spoke with another developer. He tell you what's magic. And we can incorporate this feedback from the real users to this machine learning. I think the key goal is that because we are developers, we all know what magic we do. You might use breakpoints, other might use print lines, but at the end, we have an input, we have an output, and we need to decide and look where is the bug. So I think
we are seeking the holy grail of debugging. It's like this.
So, if I may say something, so I think I have good news and bad news. So the good news, I think this is a great idea. And actually it's probably the future of debugging. Because you can actually, it's very likely that you'll be able to create systems that by using machine learning, learn to identify typical bugs. And so the bad news are in two fronts. The first one is that there are probably thousands of companies doing this already. Even Codacy, which is doing something like this, even though at a low level, very fixed patterns, but pattern finding is also machine learning. The second bad news is that this is a good idea, but it's very, very difficult to take it all the way, right? Because it's probably fairly easy to find simple bugs, and you learn by finding patterns, and the machine will learn by finding patterns, and that will help somewhat. Then it will be somewhat more difficult to find more sophisticated bugs. And then there are some bugs that are really semantic bugs, very high-level bugs, where you need to have a global understanding of what the thing is doing, and for that you need something close to strong AI. And strong AI is probably sometime in the future. But still, I believe it's an idea that it's worth pursuing. And the fact that there are probably many people pursuing this idea should not, because I mean, only a few companies will probably be successful in the end, but in the process, we'll learn a lot. So it's probably worth trying to develop this. I think it's something, because many bugs, they are on a scale, of course, but many bugs are probably findable by these sort of techniques right now.
Okay, thanks. Yeah.
If I understand it correctly, you would have an AI program to look for bugs. So the question is, what if the AI program itself has a lot of bugs in it?
That's the point when yeah, it's true, because it's also on the state of the art technology as far as we could see, like in this 24 hours or something, that this is already being done as was said. So some researchers are really deep into this, but there is the other point, which is debugging machine learning, which is also important because it's nothing is perfect, and we also had like this discussion yesterday, what should be considered perfect or not. But there's still a line of research in debugging machine learning, which I consider I guess we all consider that it's really important. So when you use the algorithms, we know that we are talking with something reliable. So of course, I mean, there is a lot of possibilities here. One startup for doing debugging of machine learning, one startup for doing debugging of debugging. I mean,
I think
we are open to suggestions.
We can convert that from a challenge or a difficulty to an opportunity, because it might be a difficulty, but it also might be an opportunity for this entity to learn with himself. So he can gain self-conscious, know my bugs, and I can train with myself. Okay. So in a certain aspect, this can be a real opportunity for him to be in a closed loop, learning, and quickly finding. Of course, I don't know a lot of machine learning and AI, but there will be a training, right? you should train this machine learning. But I think the advantage here is because you have an history of software, an history of logs, an history of stuff, so you can train them with basic stuff and validate because you already know that this bug was solved in a way.
It's like
And
history,
then
you know? It's
let
like
him
history.
go.
You shouldn't commit the same errors in the past, as
And
we
you can
human beings do.
When we can do this with open source software, just go to the history of open source software and bugs that were solved, and you can really use this as a basis for this entity to learn. And you can check, did he find the bug that was simple? And then I think also this can grow with machine learning. As machine learning and AI evolves, also this can evolve. So probably today we can only do basic stuff, but in the future, who knows?
Any comments from, Rui.
So I have been working on this for many, many years, since my PhD in Delft. I actually...
Do we have money?
Well, I actually submit a European project that includes some of these things, but so this is to say, like Erlindo said, many of these things are already been done. There are still fundamental problems with it. And one of the things that we as a community are trying to do is how to bring this intuition that we developers have. You cannot just tell some AI to learn whatever. Because one of the most important things in this loop is actually the specification. If you don't tell what is right, the AI will learn that everything is okay, except if you have, crashes. And one of the most difficult problems is when the program doesn't fail, but still doesn't follow some sort of specification. And what we have seen now is that in all this research is that we can only find small mutations. If there are small mutations in the program, then you can definitely put some AI to find it. But then when things start to be a bit more complicated with microservices, as you mentioned, things start to be really messy, and we are not there yet. This is to say that, yes, I believe that this will go somewhere, otherwise I wouldn't be research on this for I don't know, 15 years now. But still there is a long way to go. It's not even close to a startup at this point. Just a comment.
Thanks. Yeah.
So now that Rui totally trashed your idea, let's maybe go to the next. Thank you, guys. Guess that the next group is Leonid and Ricardo. So, yeah, group 7. So, I just realized that there's people on multiple groups. So instead of, there are people very creative that I have been working in multiple groups, so we have again.
Make this work in the end, actually. So good afternoon, everyone. My name is Ricardo Castro. I'm here with Tiago and with Leonid. I actually work in the space sector, and I was always passionate about space exploration. That's why I joined the space sector. And that's and after the mission of Rosetta, that was a huge success for Europe 4 years ago. Basically, I always had the idea, why don't we go beyond and beyond? Searching for life not only in the edge of the solar system, but also beyond that. Well, there are technical limitations why we cannot do that. We basically need a lot of power to send the spacecraft away. Either that, or we need a spacecraft that has very little power consumption. And also, we have the power of communication. How do we retrieve back the information that not only the spacecraft, but also the rovers or the probes that we send to explore the planets, how do we send that information back to us? Well, after the sessions that we have this week, I found some future applications or we were discussing some future applications of the technologies. Whenever we are able to have quantum quantum communication, or at least whenever we are able to entangle devices, not only atoms, but already arrays of atoms, we might be able to send a device beyond the solar system and still track its position, but also get the images that he might be receiving. With chemical computers, we might be able to send a probe to a planet, allow it to extract, to react with the soil, do analysis, or search by. We have a lot of data on the potential candidates in asteroids where to find molecular or biological matter, the beginning of life. So of course we could immediately trim and pinpoint some potential candidates. But still, with chemical computers or molecular computers, we could then send these devices to these rocks or planets or semi-planets and allow them to analyze in situ, and then with a spacecraft that we would be sending there, collect the information and send it back to Earth. So these were some of the possible future applications that we were foreseeing for the technologies that we have been discussing this week. The biggest one is how to navigate there, where we will have to pass through a gigantic asteroid belt and many other obstacles, when we really need to limit the power consumption. And to that, we were thinking of using a neuromorphic computer that would sense and actuate almost immediately. So navigating autonomously and in a reaction manner. And that's why we decided to put a brain inside the spaceship, not only because the nerves would sense and help the navigation during the path, but also because we were hoping that it could learn and be and could, with the data that it would be collecting from the different devices that it would be spreading around, could also understand what would be the possible best next place to go, or where to invest more of the resources. In the beginning of the space exploration, or for us to go beyond, we would need an independent probe to be there, and something that could reason somehow like we are used to reason. So that is the idea. The idea is to create a mission to go and explore or search for life, or to explore the outer bound of the solar system, and in the way pave or demonstrate or push for the technology developments that we have been discussing this week with applications in space. So,
okay,
if you have any questions about, please feel free.
Just one question. I didn't understand why you need quantum entanglement to get information back.
The idea was more to, when we are in Pluto, or as an example, well, when we are looking, if you want to have any part of control in it, we, mankind, we don't want to wait 1 year so that the information gets to Earth. We really want to observe what is going on there.
You cannot use entanglement for that. Physics prohibit that. So you cannot use entanglement to communicate information. So that at least
this is the, of course, that would be the
dream. This is what we know now.
Okay.
So that's the Einstein, the EPR paradox, and entanglement. Strange things happen, but you cannot send information through entanglements.
Okay. It's not to. It would not be to send. It would be actually to. If we manage to have particles entangled, in Earth and put them entangled in Earth while putting them somewhere else, we would. I know that now we cannot, and okay.
Yeah. Well, no, but with our current understanding, I do agree with you. Yeah. So entanglement could be potentially maybe one of those communication mechanisms. The problem is that we cannot control in any particular way how the entanglement will, when you do something, you don't really know in what state it's going to collapse. Yeah, so that is true. Again, we can anticipate maybe in 50 years or in 100 years we do know how to do that. Yeah, because we do see already in physics. Yeah, that maybe that measurement, for instance, should not be destructive anymore, which now it is, right? It destroys the superposition, but there are already people looking at ways in which a superposition state can be measured without destroying it. We are not there yet, absolutely not, right? So I fully, when I disagree, I say, but when I agree, I also want to say it, right? So for now, yes, we cannot do that, but it could be something that you hypothesize on. Say, it's going to be possible in 50 years. That might be, we don't know.
Let me just make, because in the space sector, whenever we dream of a mission, it will take decades to get there. But that's why we need to put there the ideas so that we can pave and try to build the technology roadmaps that will take 1 or 2 decades to go, if it is physically possible, of course.
The physicist.
Of course, you spoke about faster than light, and I had to raise my hand. Well, you are absolutely correct. To our knowledge, unless there's a loophole in the theory that we know, it is impossible to transmit information faster than the speed of light. There are a few exceptions, but it's not through entanglement. The reason is, though we can think of entanglement as a spooky action at the distance, Einstein called it that way, the thing is, we cannot code a message into the particles that are entangled, such that the collapse of the wave function when we do a measurement sort of transports the message to the other point of space. They will be correlated, but we don't have a priori no control of that correlation, so therefore we cannot code information in entanglement and use entanglement to propagate faster than light information. The other thing you said, and I didn't understand why you wanted something which is to entangle the entire ship or to entangle...
It would just be the communication. Basically, we would eliminate the antennas that we have there, we would eliminate that power consumption, and we would just have a device that would be entangled with Elvira Fortunato's Samsung panels, for example.
Just to say that it has been proven that you can actually entangle macroscopic objects, like having, it has been shown with both experimental proposal and theoretical calculations that you can have the mechanical motion of a macroscopic object to be entangled with another one. I don't know if this is useful for you, but you spoke of entangling the ship, so just to say that. But faster than light communications with entanglement, we haven't figured that out, and I don't think we're going to get it. Okay?
I'd just like to point out that there was this idea had a lot more. It was not just about quantum communication.
So the telecommunication was just the part to make it as well. It would be the wow factor when we reach somewhere to be immediately. But also the. But that wouldn't eliminate the problem. That was to eliminate the problem of the speed of the telecommunication.
So I really applaud your ambition to try to move beyond where we can go right now. We can go within the solar system. We've gone to Pluto, but we now discover planets around other stars. But they're really along even the closest stars for more light years away. So why not, I'd say, by all means, keep pushing this. Put in neuromorphic computer in a probe, send it out as fast as you can with whatever propulsion you can, and put in human consciousness into that computer, will be gone as a human being. This Earth will disappear, but that probe will keep going and eventually go somewhere where there may be other civilizations. So it's a way of perpetuating our consciousness, if not our bodies.
Just one comment on the other. I'm sure you are familiar with the concept of von Neumann probes.
Of what, sorry?
Von Neumann probes. So your idea could probably be use that concept of von Neumann, which is basically all you have to do is to build the first probe that can reproduce itself and send out probes, right? Then you have an exponential explosion on the number of probes. Even if it takes millions of years, eventually take care of the galaxy. So that, of course, plays well with your idea of a chemical computer and of the probes that can reproduce themselves. So that's a great idea. And I think we can do it. Sometime in the future, we'll be able to do it.
Well, I didn't mention that. Of course, this would need as well, in the European Space Agency, we are working on electrical propulsion, and this would need very strong advancements in that area, for example, to make it feasible to even to reach in.
Well, I mean, the good news is
the other part, but yeah. People are actually working on not on this, but on similar things. Also in situ resource utilization, which goes to that area, but that would increase the mass of what we have here, and yeah, this can lead for several speculations. And
if we can reduce the mass of a probe to just a few grams, we can accelerate it to a high velocity, which is to me that's the answer.
So, any more comments from the audience? Any alien in the audience? Okay, thank you.
Thank you for your time.
So now we're going to have group 8. Oh, it's you again, yeah.
This, no? Oh, no, okay. Oh, just want to reveal the idea. This is before PowerPoint. So I was very inspired by the talk about neuromorphic computing and the way we could mimic animals, and with very domain-specific computing or processors or neurologic processor, we could mimic nature with low power. And so I was inspired. I was thinking on birds. So birds are here a long time ago, and they could navigate. And they don't have Google Maps, neither GPS, and they can still navigate. So pigeons can go back home. And this was used during the war times or to transmit messages, but the pigeons would go back to their own place. Or even with storks that migrate during the winter, and they come back to the same nest that they left. So they must have some kind of GPS, or more biological GPS, that we don't know. And this started like this, and I made half an hour looking at papers, and I discovered that this is recent research, and that's why I'm here. I was dazzled, and you're going to see the serendipity, because I started with the neuromorphic stuff, and you see where this will end up. So I found out that this being studied for a long time, so people thought they have some kind of compasses or something to know the localization. People thought they could have visual memory of the field and could memorize landscape. But find out that there are three main
areas or mechanism that birds use to navigate. I will start with the simplest one that is covered in pigeons. They have some balls of iron material that can detect the north, and this will help them to find like a compass. So this will help them to find the north. But incredible, they find out there are some cells that have some magnetic reaction material, probably iron or other material, that this can tell them what is the latitude to the magnetic field, so that the angle to the magnetic field. So this will allow birds to know what's latitude on Earth they are. But the incredible part, it's the third one. So they also, there's something missing. So they discover on the bird eyes, they discovered a protein that reacts to light, so chromoprotein. And with experiments, they discover when this protein is excited by light, it generates two molecules that are entangled, quantum entangled. And what they discovered that these two molecules that are entangled, they are used to determine the deviation of the magnetic field. So they think that birds, when they are stopped, if they turn the head, they can see patterns of difference of that magnetic field. So if you start crossing all these three, so you see that we have three. So we have a compass, we have an angle, latitude to the magnetic field, and we have another angle, it's the deviation of the magnetic field. So if you look at GPS and how we do positioning and navigation, we need triangulation. And you see that nature find out a triangulation way. You have three variables, compass, an angle, and another angle. So you can draw triangles, so birds know where they are and where they need to navigate. And this starts because I started to talk with Sarmento and start to pumping up ideas where you have three technological areas. One more short term, it might be the compass. So you might think on neuromorphing compass, and this could be used for low power systems where you have a need to identify direction, so probably to complement GPS or other applications. And you have a more medium-term area, it's knowing the angle to the magnetic field, so knowing the latitude. And the more long-term, it's how investigate and research how this entanglement is made to measure the deviation of magnetic field, and this could be used for, I don't know, medical application. So the immediate reaction, okay, we can have a GPS complement technology, low power. We can even think on replacing GPS. Why we're spending money in sending satellites to space if we can look to biology and have devices that could do the same thing, or even navigation alternatives or medicine. So this was really where I stopped in half an hour now. Imagine if we could have researchers looking for these three areas, because it was really three different areas. So one more chemical, another one more neurologic, and the one it's with quantum. So it was really serendipity at the end. So I started with something, and then, whoa, I'm the right conference.
I think.
So we only need two angles, right? So we have a fixed, so the north. One angle is the latitude, and the other angle is the deviation of magnetic field. So you have two angles to know. And you could draw a triangle and know where you are. And I think this is late research. It's a paper of 2018, so really, and I was imagining building prototypes to test this. It was easy. You can use a drone or a balloon and try to navigate. I know that there are some guys experiment with pigeons where they try to hide the magnetic field, and they induce magnetic stuff, and they see the pigeon do some behavior. So it's very easy to start prototyping with this and starting testing behaviors. I don't know if this is allowed in Europe, but they cut the connection between this sensor and these neurons, and they could see that the birds would not know where they are, but they could detect the North Pole. So there is a connection between these sensors and these ones, but when they go together, they can have a reference point. So it's very interesting material there.
Actually, I don't know if you know, but fun fact about pigeons, they're actually kind of the forgotten heroes of World War II or something like that, because they were trained to pinpoint like the locations for bombing. So instead, before there was GPS, and there were actually, I don't know how many medals given to pigeons during that time.
And there's another interesting factor, pigeon. There is a very well-known RFQ that is Internet over Carrier Edge. So you can look at it. It's people that say that they can send IP packets using pigeons. And there were some Finnish guy that in one day they tried these experiments and they made it. So they print the packet, send a pigeon, then they digitalize the packet, send the pigeon back, so they have a round trip time, but they could prove this. So pigeons are long in history of technology.
It's a super interesting idea because it is, and I only want to make a comment because I don't have actually many questions, but we do discover that quantum physics and quantum phenomena are omnipresent in nature and in our own lives. So the fact that a bird has that particular feature is not a big surprise. The fact that they discover it is, of course, a big surprise. Yeah. But this is something that we already know. Yeah, the green, the chloromorphic things in the leaves. These are all quantum phenomena that we see happening. Yeah, so that it's very interesting, actually, this idea that we should start, really investigating in that direction.
It could make sense because it will be a very sensitive machine, right? Because the magnetic field is weak, so it's really a sensitive machine that detects small variances on a magnetic field.
Yeah, I think this is a really important idea because by nature, GPS signals are very, very low power, or below the noise level, in fact, but it's such a successful technology that governments are switching off all the alternatives of navigation, like those of you who are in the airplane business, the microwave landing system, LORAN, Omega, they're all being switched off because they say, why have these others when GPS is free? And the answer to the Air Force is that, well, don't worry because we have the European Galileo system, which when it comes on, it'll be but it's also very fragile, or it can be fragile. So we're putting all our eggs in one basket, and that's makes me very nervous. So if there's any way that we could come up with an alternative to GPS, it would be very useful.
I think there is another important factor of GPS because it's owned by the military, but they say they can claim you can use for free.
They can shut it off.
But they can, instead of shutting off, they can degrade the signal quality. So during the Iraqi war, they did this. They degraded the signal quality, so GPS would lose accuracy.
Well, I don't know exactly what the details of Galileo, but the Galileo system is being sold as an alternative to GPS.
So I have a kind of question.
Yeah.
I think this idea is very interesting, especially because when we think about GPS, we think mostly about surface navigation. So we're talking about on land or on air up to a certain height, and that's it. And that's only maybe 10% of the entire Earth, because most of the Earth is under Earth, and we still haven't discovered that, and we still haven't made almost any exploration below the sea, right? So there's huge amounts of possibilities for using a navigation technology, which does not require satellites, right? Because we cannot get that signal 10K under the sea for sure.
Because after I talked with you, I was going to look, can we detect the magnetic field underwater? And then I discovered that they find out that there are some fishes that use echo navigation, but they find out that stingrays, they use magnetic navigation. Then they use this to detect the landscape of the sea, because it's like a bat, but under the water. So it's really, now 1 hour. What?
Can I make one small comment? One of the interesting things, and it was just mentioned, is that we are now discovering that nature, first of all, it's very economical. It doesn't like to spend energy. So it naturally, through evolution, has found processes that are economic in energy and are efficient, right? Just to give you an idea, you spoke about entanglement. There are now people who suggest, and there are some results that go according to this, that chlorophyll, in its process to capture random photons that come from the sun, somehow uses entanglement and some form of quantum synchronization to take the energy of different photons, synchronize it into an energy package that goes through the molecule, like the electron cloud goes through the molecule with an energy package, and then has a synchronous deposition of energy on the ADP to produce an ATP, so to store chemical energy. Okay, so one of the interesting things that physicists and biologists and scientists are looking at are the relevance of quantum processes in nature and the complexity of those processes in nature and how nature uses those quantum, chemical, whatever processes to produce the maximum benefit, the maximum whatever, with the least energy. So I think one of the interesting things that you pointed out as the need to go to nature to get inspiration and to understand nature, to get inspiration from nature, and see how we can be, to use that intelligence, okay, to make our systems more efficient.
That's okay. It's right. I just discovered. I think there was an experience where they tried. I think it was pigeon that identified it's only 53 neurons involved in some of this process. So it's not the complex machine to do this, right? I don't know how far the research on that area, but I saw an article recent that they could identify 53 neurons involved in this process.
So I think we need to fly away from
Yeah.
this presentation.
Yes. Thank you.
Just a final comment. A pigeon should transfer data at 2 megabit per second, I think. It should be possible today.
2 megabit per second. Okay, so our next speaker is going to be the role of education, yes, in the future of computing. José Sérgio Matos. Just to kind of give you an outlook of what's going to happen. So we got this presentation and then we got another one. So just two, and then we go for the break. Okay, so I think this will take us about 20 minutes or so, a little bit longer, maybe. About 20 minutes. Want to go? Yeah. Sorry guys, just a couple more minutes. That's why we like paper.
Okay. Já está. Ok. Já está. Well, I apologize for the long presentation since I didn't have the time to reduce it. So we are talking about group 21. I'm adding 10 plus. In this case, I started to work on this project since the morning. So there are a few shortcomings, and I hope with you to improve it. So my idea is that about the role or the roles of education on the future of computing. And in order to do that, I will talk about three things. The motivation, some kind of strategic analysis on this, and then a more tactical approach and what to do next about it, okay? So in terms of the motivation to this project, I should tell you that my background is in physics and applied math. I am also on computers, on scientific computing. I teach at the Faculty of Economics, in this case of all three levels, calculus, math at undergraduate level, in this case with the help also of a computer algebra system, maximum. And also I teach numerical methods for economists in the master, and computational economics at PhD in economics. Also, I participate in the PhD program in applied mathematics from the University of Porto. So this is my background, so that you know where I come from. And the idea, what did I notice? I noticed that students, both from economics and from applied mathematics, they like some of the basic knowledge, education, training, whatever, in a basic set of computational tools and techniques. For example, control version. The idea is, as they do control version now, is to append 1, 2, 3, and then final version 1, 2, 3, 4, and so on. So come on, we have solved that problem has been solved for a long time. So those are some of the problems. Also at the same time, we want to be able to do reproducible science. We want to reproduce the results, and usually that's not something that is easy to be done. And at the same time, I also noticed that in the university, students are not used to work with large or distributed teams. Usually they do some works with small groups, but they are not used to work in large teams. And as we saw in some of the presentations, the future, in a sense, or for most of these problems, are to work with large teams. So that can be a problem. Also, at the same point, we are introducing or we are coming with some solutions that have been developed a long time ago. So there is some slow adoption, some kind of just like a fluid that is very viscous, and there is a slow diffusion of the technology. And as I said, even students for whom the computational aspect is crucial, because they do simulations or things like that, they don't have this knowledge. So that can be a problem. We can have very good tools, very good machines, and so on, but the students don't know how to use them. So that was the problem that I saw. So if we try, and I tried with the help of Luis and Ariel and some other people, to identify some of the possible problems, some kind of strategic analysis using the SWOT analysis that you know that stands for those 4 letters. And we tried to do some kind of simple and naturally incomplete analysis. So one of the strengths of education is that we have a long historic record. So we are not starting from the beginning, and we also have, and this is an active area of development, several methodologies to work with adults. And our students that we are working are adults, so we have several ways to engage them and for them to learn. So that is the purpose in education. We also have some weaknesses, several of them. One of them is that we are accused, and that's true, of not reacting quickly enough to the changing environment. As several of the speakers said, things are changing very rapidly, and we are not adjusting enough to that. And also, at the same time, one other problem is that the knowledge areas, they are compartmentalized. There are physics, there are math, there are computer engineering, then there are computer scientists, and they are all in their niche. That is a weakness. But that also comes with some opportunities. And our opportunity that we have now is to empower users to take advantage of the tools that have been presented here. That is quite interesting, and in the speakers that we heard, we saw that hope that we can fulfill that. That is quite important. And at the same point, some of the methodologies that we saw, they can serve as some kind of motivation. Even if they don't have any immediate application, that can be served as a motivation to do something better using a different point of view for current problems. Also, there are some threats here. There are many sources of knowledge. If you go to YouTube or wherever, you know what I mean. And there are very few curators of those information. What is the information that is more relevant, what is not? And sometimes due to institutional inertia, institutions move very slowly, and probably they will do so in the future. That can be a problem. So those are the threats. As I've told you, this is an incomplete model, and we are trying to propose some kind of solutions for this. So in terms of the users, we should recognize also that not all users will care about the low-level detail, from the machine, from the circuits, until the operating system. So we need to develop new tools and to diffuse that knowledge. That is an important part. To is in this case, the collaboration work. We want people to collaborate to improve the visualization and the specification of problems. We should help us to create some domain-specific languages that help non-specialist users that are not specialists to be able to formulate the problems in order to be solved. And at the same time, for example, in the actual curricula, we want for those tools to be used on the current curricular units, and not to put that apart in some separate curricular unit where people don't interact, because then we will have more of the same problem. So, and at the same time, something that we thrive in university is not just for knowledge, but also to change attitudes and behaviors of the students. So we should try, and this is becoming cliché, to favor an eagerness for learning new subjects, because the environment is changing. And also we empower our students to know where to find the new subjects. And we should try to lower the barriers to change to new areas. So the proposal, instead of discussing these genres in a general context, is at university level to provide a free course, summer course, winter course, wherever that is, because it would be very difficult to do that, or it can be very difficult to do that for the official curricula. So the idea is to provide free courses on computation to provide some of these resources. So the idea of this project is that to create courses where there is an initial and introductory module that has the objectives of the course. And the idea is that after this initial course, we present them, we ask for the participants to propose some kind of problems, and for them to take that problems in teams and to try to solve them. And what we try, instead of solving in one way, we will try, after the initial specification of problem, we'll try for them to try 2 or 3 different ways to solve the same problem. And then, if possible, we want for them to compare their different solutions and implementations. So in order for them to learn with each other and to see how some of those tools that they probably don't know, how they can be used. So that's it, most.
Thank you very much for very interesting set of slides, 17, oh, okay, 16. Yeah, but I hear those stories so many times, with all respect, so I'm not insulting anybody here because I gave exactly the same kind of blah, 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 yeah, whatever it is. And the only thing that I now, at my age, yeah, when I talk to younger colleagues, like sitting next to me or whomever, yeah, I said, no, I want to hear what you're going to do next academic year, one course, and what are you going to do in that course that really will make a difference. I don't want to hear about the users and whatever it is. Or like, whoa, whoa, whoa. Nobody feels responsible for what it is that you're saying. So I want to simply hear, okay, whatever in the summer school or the winter school, what are you going to do that changes that? Maybe you don't know now, but that's maybe the simple, that's the message that I want to bring, because I'm not interested, me personally, yeah, and in Delft, there's like the blah, blah, blah that everybody, yeah, sure, we know that, yeah. No, I want to hear one concrete idea and then understand, okay, now and then hopefully motivate other colleagues to do, I'm going to do that too. And that's how you create real change.
One problem that I noticed, for example, with master students, when they are presenting their work, initially we did that with Octave and MATLAB. That was the ideas. And for them, it were quite difficult to create a report at the end. So what I will do this year, for example, at these master courses, I will introduce, I will have them use Jupyter notebooks, for example, where they can mix the explanation with the results, and I can rerun the notebook to see if they understood the problem and if their solutions, if they are able to put in practice this. So that is a change that I'm intending to do next year.
So I think it's a very nice analysis of the current situation. And I think it's still, people don't understand it at the moment, that we are, I think, at the transition of education. And it's important now to change our way to educate. And I think that you really presented very nicely and analyzed it very deeply. And I think, so we can see why people have not understood it. It's just we need a lot of money to do that. I think a huge amount of money is needed, and the politicians, decision makers, either they don't understand or they don't want to understand. So that is why I think it's still important to analyze the situation and find out whether this is really true, and I think it's true. And I mean, to change things we need a lot of resources to do that. And of course, and there are a lot of ideas how to do it, but people in education, they are extremely busy with a lot of things like teaching and administration, and with administration and administration and so on. Yeah, and so we need really resources to allocate to change this now. And this, I like it very much.
Okay, thank you.
Yeah, there is, thanks. There is maybe one of the possible answer to that question is mathematical. And maybe we can look, we are already doing it actually, we teach linear algebra the first year, but maybe we can look deeper into those structures that are common to all or most of our fields and try to start and to teach that as a common basis, not only for engineers actually, because if we can shrink things down to something that's essential to to modern day technologies and so on. Maybe you can do that from a mathematical point of view, maybe with some algebraic analysis on the kind of object we manipulate.
So now I'm actually speaking as one of the organizers, and I think I will speak for all the organizers when I say, well, we agree with some of your ideas, if not all, but we agree with your analysis. And I think when we first thought of this school, we were looking in the same general solution, general direction. So what I would like to say is, can we keep a copy of your presentation?
Yes, you can.
And that's the best compliment I can make.
Thank you.
A very, very nice presentation. But just to say that when I entered this university, or the second time I entered this university, I entered the Faculty of Engineering. And we had, in the first month, was dedicated back then to the FILP project, which was a small project where we had to present, we gave a presentation, and basically it was intended to stimulate in us some soft skills that engineers are not that much known to have. However, there are some art skills that probably could be as widespread in such an introductory course in university, or some good practices that could be fostered. So probably as an entry point in the university, some of your ideas could be applied.
I'm kind of passionate for this subject of education and sorts, and I'm very skeptical on our current education system. I think it works randomly, in not on most of the cases. So what I have seen is that we, as you said, we teach in a very strange way. We divide things. Like now you need to know physics, and now you need to know mathematics. And they're all kind of the same thing that you need to use at the same time, but there are two different teachers that teach two different ways, and they do not mix. They, most of the times, are not even friends, as in they don't like each other. So one of the challenge, I have two kids, and I was trying to find a different approach to their education. And there's a trend in education in Northern Europe which is kind of focusing more on project and abolish every subject. So I think that's what we could try to prove that works here. They also already proved that it works, but Portuguese don't care about that. So let's try to prove here in Portugal that it works. So with that course, forget about the subject, forget about the theme, forget about the problem that you already know the solution, and focus on a problem that you don't know the solution. And ask for help for other colleagues, and try to figure out a real problem that is interesting both for you and the students. And maybe then you can try to convince other people to try to change that. That's my suggestion.
One of the problems that I saw is that, for example, I'm able to do metaprogramming using templates in C++. And that's cool, that's really cool. But when some of my students, my PhD students, can do the simple things, then we have some kind of a gap. And the idea of this project is try to close some of those gaps. Okay, so I agree with you. We changed, for example, in the works in the master, initially we had some kind of problems with some kind of items for them to solve. And last year we changed that to a problem that they should try to solve in their own way, and they get lost, okay? So the idea, if you try to divide the problem in subtasks and so on, they will try to do them the same. If you don't give them that guidance, they will feel lost, and so we should always try to, so I'm just saying that it's not easy at all.
Because we're taught to, given a definite problem, a very scoped problem, to be taught how to tackle that problem. And we should be taught how to study to understand how to tackle it, which is completely different. So I think that's the main issue there.
Yeah, but the problems are the fine details, as you know.
Since people are so passionate about this topic, I'm going to extend a little bit more the question.
Sorry, I'll be brief. Fatima Sonsimão, I work at UP Tech, and we're organizing this because we also feel a lot of the problem you've just presented here, so we're totally in tune with you. And one of the things that, two things I want to say. One of them is consider involving other disciplines in approaching this, because we've been working on that in the past years, and it's proven very interesting, and the results are very exciting as well, both as a process and in the end results that you present. And the second thing is that because we identified that this is not only a problem inside the university, but it actually has effects on how these people that leave the university then work and then relate to the world and eventually do business, which is something that we are also working with. We've redefined our strategy last year in the sense that we want to get closer and closer to the university to the extent that we can help do this brokerage between disciplines and between the university and the market. So please do use and abuse of our services, because that's what we want to continue to do. Thank you.
Thank you.
So one last question or comment.
Well, you made very, pretty good points, some of which I share and have even included in in research and pedagogic proposals in applications to professorships in Portugal. So it was good to see, recognition from other people as well. But concerning, for instance, the courses that you mentioned, that you suggested that should be free, I do not agree with that.
No, sorry, what I meant free courses, that means that they are independent from the official curricula. Those are called free courses because someone can participate, and I'm not discussing the price.
That's the thing. Courses or even consultancy services could be extra sources of revenue for universities, right? And that would give, strength to researchers, and also, it would stop giving universities the excuse not to hire researchers for lack of funds or things to do or whatever. So, and it would also connect universities with industry or private-owned services.
That is one future avenue, but
exactly, that's a win-win situation for both. Yeah, thanks.
So I know that I'm a horrible person, but I have to shut this off. So let's go to the next speaker. Thank you so much.
Okay.
So our last presentation is by Ken. And has a long title. I'm not sure if it changed.
It's a joke, but yeah, I guess you can.
Okay. So general continuous discrete model for allegedly closed complex systems, or how I learned to stop worrying and love the turkey.
Yeah, or maybe somebody to hold these. It would be good, some collaboration, because I can't, sure. Let's see if this device works. If the paper stays on the board, I think I'm cool. And I had, sorry. Okay. So first of all, I want to thank you all. It's been I'll try to be brief, but I really want to thank you all for your openness. It's been a really stimulating week. I'm not a researcher. I work in IT. I'm a data scientist right now. I'm Italian. Been working in Portugal. I've been living in Portugal for 10 years. I have a past as in humanities. I took a philosophy course, and then I took applied mathematics at IST in Lisbon. So I always feel that my background, a mixed background, is something that I can always leverage on, and especially in a like more engineering environment. So this is what I'm going to do today. In the end, I'll try to build a chemical simulator for a quantum computer. It doesn't work, but it was an interesting game to play. But I'll start with the turkey. I think some of you or most of you already know what I'm going to talk about. This is a scientist turkey. It's a very rare breed. And this guy every day, well, he started, one day he got out of the turkey house and he saw that there was some food on the ground. So he said, oh, wow, this is so cool. He ate the food, and then the next day at 9 sharp, he got out and there was some other food. And the turkey thought, hey, I'm seeing some kind of pattern here. So let's try to get out tomorrow at the same time. And so the next day at the same time, there is some food there, and so on and so on. And basically, the turkey said, there must be some kind of law in the universe where if I get out of my turkey house at 9, I always find food outside. So he's really happy about this discovery, and he lives a happy life until, I think in the original story, I think it was Christmas comes. And so he got out of of the turkey house at night, and he got his head chopped off, and he went to the oven. I'm a vegetarian, but sometimes I eat turkey, so most vegetarian. This is not from me, it's from Russell. I hope most of you already know the story. This is something that comes from, it's a really good description of the limits of scientific inference. There is always the possibility that our system or our theory does not work. The idea of a controlled experiment is a nice rhetoric argument. It's a nice rhetoric instrument. As somebody already said in the last few days, every part of the universe is connected with everything else. And so there is no real isolated system, as people from quantum mechanics know. So we must maybe have a closer look to what we mean by having a theory or having a model and working with that. And some of the things I'm going to say are already being discussed during this week, but I'm going to touch some of those. I want to add something that was, I think, crucial to the last weeks and crucial to the last few years, and that's about complexity. So if I'm describing like a body, a mass that falls on the ground, I have a relatively easy equation or set of equations. I kind of, let's say that the rhetorical power of my description of the object that's falling, and so the mathematics that I'm applying, it's quite high. So every other human would say, yeah, that seems something that really works, and you convince me. There is this problem of persuasion that's related to science and that we usually don't think about. Now, I will just mention DNA, but we have AlphaGo, human brain, and so on. So on one side, we have the problem of black boxes and all those algorithms that work just because they work. There is some heuristic there. We know how to train them. We kind of know what to do to them. We have some hunches of, for instance, how many layers put on a neural network. We have maybe a general mathematical framework or background to describe them, but usually we don't have a hard mathematical theory under those. And at the same time, there are those systems that are just too complex to model or too complex to think about. We mentioned the tens of thousands of proteins that the DNA code and the tens of thousands of interconnected relationships that happens within a cell. Same apply to human brain. Any kind of actually graph structure, it grows in complexity really, really fast. So what I have next? Yeah. So this is something I borrowed from Professor Cardelli. I wrote the names. And it's, I took off most of it, but I think this is crucial. The Turkey at the beginning, and these are the main slides, material slides of my presentation. So the thing is, we cannot be happy as the Turkey is. Not in the same way. We cannot forget that there is a social, historical context there is to science, to science research. Science does not happen in a lab. There is an economical context also to science, as universities know really well, education, cultural, and so on and so on. Science, if any, science happens within a community, so within our community in this case. And I put people talking, and I put a banana. The banana is just a symbol of our animal side, of being creature of irrational creature in part, creatures of desires, creatures of, we have some primate hierarchies that are still there. And I'm taking these, let's call them metaphors from biology, just because for you it's easy to grasp what I'm talking about in terms of context. So maybe we have something that goes around between a model and a system, or between a theory and nature, or something like that. I don't really know what these arrows are. You can decline them in different ways. Probably none of them will ever be completely satisfactory, or so completely descriptive of what's happening here. But the point is that we are in the middle. So please, if anybody is already telling their students that there is something over there that we then discover and observe, and then the thing, we know how the thing is, that doesn't happen. There is some atheists or some rationalists, they have this nice argument against religion, and they say if we delete all the religion books, in 100 or 1,000 years, nobody will ever remember about Buddhism or Catholicism or so on. And they say if we delete all the scientific books, that's not true, and we will have, science will happen again, we will discover atoms again, and so on and so on. That's just not true. It's purely not true. Atoms is a Greek word, it has an history, it has an history in the history of ideas. Most scientific discoveries, all scientific discoveries happen within a context, within a technological context, a cultural context, a linguistic context, and so on. So let's look at things, let's be smarter than the Turkey, if that is possible. Okay, I'm going a bit rough here. I was not, yeah, I have to break. 4 minutes? Oh, wow. Okay. I have to say something about the social context. This can be hard for some people, but I think it's something that's worth saying. So science can be seen as a rhetoric instrument, as a persuasion instrument, a really strong one. And we are seeing any kind of abuse of science as a rhetoric instrument. Those pseudosciences, like chemtrails debate or climate change deniers and so on, people that denies evolution. I put Apple here because I don't like expensive computers, and I put, this is a social issue that also touches science in some ways. Again, you can take it as a joke, but it's still related to our context. So I'm linking to what we said just a few minutes ago. We have a pedagogy problem in general. We should probably touch or remind ourselves that there are some phenomena, including the actual scientific researches, that are not reducible or that are not simply theoretizable or transformed into something static. Music is a good philosophical example of this. And of course, this has already been discussed by the previous, my colleagues, so I'm not going to talk about the needing of a pedagogy. Okay, this is also quite rough, but this is something that not you as a scientist, but us as a community have to think about. So other pseudo-scientists and heuristics, I put a tarot card here, I could put astrology there, and I could put, well, this is just a guy meditating. I personally like it. I don't know if that applies to science, probably not. But still, it applies to our context. And some of the contextual things that we ignore as a community will affect us. We have already seen it, like problems with vaccines. Okay, I'm going to do, can I have like 3 minutes to do a quantum computer? Yeah, I'm done with this.
If you can build a quantum computer in 3 minutes, I think we can win.
Okay. So based on this, so if there is an irrational basis if we cannot infer everything, or if inference is biased by itself, we can assume that there is an irrational basis to our actions as humans and as societies. So I can pick whatever field I want, I can pick whatever theory I want, and work with that without having to persuade myself or people around me too much. It's not about being scientific. Well, it is about being scientific, but it's mostly about getting funded and convincing my teacher and so on. So what I did is I used the model of a chemical network or a reaction network. And I tried to model a quantum system out of that. I didn't really get there, but let's say that we have 2 qubits. I call it alpha and beta. And we have only 2 operations, another mark gate on the first qubit, and we have a C0 that runs on the first and second qubit. These are the only operations that my machine can do. Of course, it's not a universal computer. Now, I can look at the possible output states of this system, and so if at the end of my whatever, of my computation, I measure it, then I have something like this. Okay, I can call those states A, B, C, and D, and I can borrow the graph we've seen the other day. So let's say that if I start from A, and I apply another marked reaction, let's call it a reaction, I can go to state C, and I have some probabilities that I'm still in state A. I can do the same with the C0, and I go to, this is active, so I go to D. And I can do the same on the way back. And finally, I can apply another mark here and go to B, I guess, with some possibilities that I'm still in D. And these operations, they can go the other way around. So I have a control problem here, but I don't know how to build this. But if I find the chemical species that do this, in the right proportion, I can do something like that. This is not completely true, because here I'm going down to a description, a probabilistic description, and quantum states I've discovered this morning. Just they have a third. They have the phase that cannot be described by possibilities or by probabilities. But if I have arithmetics, I can build algebra in chemistry, and if I have algebra, I can build linear algebra. So that's it. I don't know how to do that, but maybe we can speak about this. Thanks a lot.
we don't have a lot of times for questions, but since we have here some quantum computing experts.
I was already discussing this thing this morning with him. So just to summarize, so what you were trying to do is to model the model of quantum computing based on these chemical reactions, right?
Well, based on these, I don't know what the underlying structure should be, but based on these kind of chains, yes, based on this graph structure.
But what would you gain from that? I mean, what is the purpose of
it? Works at room temperature. If chemical people provides me with the right components.
Okay, but we also say that.
And you can observe at the end you can observe the concentrations, and you have your probabilities already. You don't have to repeat the experiment several times.
Okay, because everything boils down to the probabilities, right? Instead of working on, let's say,
the
computation.
You need a control system so that you apply the right transformation or the right reaction at the right time, and eventually you'll have a probability distribution based on chemical species, and you map them to quantum states, and bingo, theoretically.
Okay.
It explodes, of course.
Yeah. Actually, it is a nice idea, because actually one of the colleagues in QTech in Delft, he has done his PhD working for IBM on doing the factorization of the number 15, so getting 5 and 3, using chemical processes. So actually, it's not that far-fetched as what you might think. But then now I'm talking, it is already like 15 years ago. Yeah, and so now he's into semiconductor qubits. So, but definitely this is one possibility to go in quantum. But don't ask me any details, because I'm completely ignorant.
Thanks.
Okay. Oh, the physicist.
Yeah, physicist. I'm so sorry. Okay. So I don't think that's a quantum computer. It's probably a chemical computer, sure. It can be a quantum computer in a broader sense, that there is a quantum description which takes probabilities and stochastic calculation integrated with quantum properties. But most probably you would lose the superposition by having a statistical component. Having said that, and the next comment is not for you. It's a very general comment. You don't, to make a good information system, a good computer, you don't need necessarily to make it quantum. I mean, quantum is not that miraculous word that, okay, I have a problem, just make it quantum and it goes away. So feel free not to use quantum, to explore your ideas out of quantum, and they might work very well. Okay, most probably quantum have a specific range of application, and it will be very good at this. This is what we believe, but quantum is not the solution. It's not the magical pill that will solve the problems of the world. The engineerial, the problem-solving aspect is to know how to apply the best tool to do the job. And that means not being focused on one type of approach, but I think we've learned very well during this week. Look far for different solutions, different approaches. They will bring a contribution. And I like the idea, precisely if you take the quantum out of it.
Okay.
Okay, thank you.
So if there are no more questions, I'm very happy to announce that we're very exact. We're exactly half an hour late. So, which means that I'm not sure about, so first of all, thanks. Thank you. So my suggestion, if that's okay, if we start at 5, the presentation instead of 4:30, if that is okay. Yes. So then let's have a break, half an hour, and then come back at 5 for Professor Lindro's talk. Thank you. And thank all the hard workers hardworking people that helped creating this hackathon session. This was very experimental, and I think we had pretty good results, amazing ideas, and I hope we can develop these works a little bit further after this school. We should keep in touch. Thank you.